Hello everyone, my name is Sushil Deore. I have been student of Liverpool John Morris University from past 6 months. My topic of study is multitask learning for predictive maintenance applications on class imbalance data. So this is the agenda for today's presentation. We will start from background of the study, literature survey, problem statement, methodology, result and discussion, and finally conclusion and future works. So, background of the study. With newer methods and IoT development models being created and implemented, day by day more research is coming up to look into predictive maintenance in manufacturing industry. This study is focused to develop more reliable solutions towards the continuity of tools, equipments using state-of-the-art methodology. To stay in a competition of global development, organizations needs to adopt newer possibilities and newer technologies. Machine and equipments play central role in organizations' needs and prosperity. The cycle of development demands more from this machinery and equipments. Hence, topic of machine failure and machine maintenance also appear to be important. We have type of maintenance over here in the figure. First is reactive maintenance. In a reactive maintenance, repairs that are done when equipment is already broken down, in order to restore the equipment to its original operating conditions. Reactive maintenance is done. Next is preventive maintenance. It is a scheduled maintenance activity to help prevent unexpected failures in the future. Next is a predictive maintenance. It is a maintenance technique which is designed to help determine the condition of the in-service equipment in order to estimate when the maintenance should be performed. We have multitask learning over here. A multitask learning is a standard training construction in which machine learning configuration is trained with different tasks concurrently. Next is auxiliary learning. It is a method to improve the ability of primary task to generalize by training the additional auxiliary task alongside this primary task. Literature survey. These are some base papers. First, handling data imbalance in predictive maintenance for machines using smooth-based oversampling, published in 2021. In this paper, the development of machine learning algorithms for the prediction of machine failure is done. A synthesized dataset was used in predictive maintenance model that reflects real-time failures and encounters in the industry. The class data imbalance hinders the performance of machine learning algorithms, and this is handled by evaluating smooth-based oversampling technique. By using smooth technique, a 7.83% increase in AUC score is observed, thereby improving the performance of the random forest classifier in distinguishing the instances of non-failure and machine failures. Next is a brief review of deep multitask learning and auxiliary task, published in 2020. A brief review on a recent deep multitask learning approaches, followed by methods on selecting useful auxiliary tasks that can be used in deep multitask learning to improve the performance of the model for the main task. Next paper is Explainable Artificial Intelligence for Predictive Maintenance Applications, published in 2020. In this paper, two methods to provide an explanation for classification result is given. A complex ensemble classifier is evaluated on synthetic predictive maintenance dataset. Both methods have inherent strengths and weaknesses, but provide an overall benefit for the user without high additional cost. The explanations provided by the decision tree tends to be higher quality, but in a considerable number of cases do not provide any explanations. On the other side, normalized feature deviations provide explanations of consistent yet slightly lower explanatory quality. Next is a brief review on multitask learning, published in 2018. In this paper, authors have briefly discussed the motivation of multitask learning, review some current multitask learning methods, and compare their formulations. How neural network or deep learning can be used to solve complicated multitask learning problems and some of the useful resources. tools that can be used to help us implement codes to implement MTL problems. Next is problem statement. The detection of failures and flaws in manufacturing tools and equipments has demonstrated to be a challenge to scale its assurance and execution. Deflection in manufacturing tools and equipments takes place owing to many elements, generally tool wear, strain, heat failure, and power failure. The aim of this study is to determine the machine failure by construction of a classifier model on a predictive maintenance dataset. The class imbalance data compromises the performance of constructed model, and this addressed by assessing the oversampling methods with multitask learning architecture. Also, to gauge the performance of auxiliary learning toward the advancement of the primary task. The cardinal aim of this study is to determine the machine failure by construction of classifier model on a predictive maintenance dataset. Another purpose of this study is to solve the problem of rare event class distribution in the dataset. To explore and implement multitask learning, considering classification of the machine failure as a primary task and reconstruction of the input as an auxiliary task is the goal of this research. We have defined some objectives for this. First, to analyze the framework and correlation between factors affecting tool life via visualization to enhance the understanding of machine failure. Next, to advance the suitable balancing technique that can be implemented on a rare event class dataset. Next, to examine the performance of multitask auxiliary learning model to segregate machine failure occurrence based on characteristic attributes. And last is to gauge the performance of the model on multitask learning and benefit of auxiliary learning on a primary classification task. Methodology. The goal is to identify machine failure by construction of classifier model on a predictive maintenance dataset, using machine learning models and artificial neural networks, evaluating the obtained results and deciding which model architecture perform best on the chosen dataset. The previous relevant research on this dataset used various mode-based methods and explainable artificial intelligence. The class data imbalance hinders the performance of the model, and imbalance is handled by evaluating mode-based oversampling technique. This research work proposes to use multitask learning and mode-based oversampling, which will help to classify machine failure instances and generate instances which will help to predict the future machine failure. This work has added advantages of model generalization, which is counter to overfitting, model efficiency improvement, and next, fast learning by leveraging the auxiliary information. Next is dataset description in methodology. We will start with dataset location, its configuration, and the relevant part in this study. Dataset contains 10,000 rows and 14 columns, where only 9 columns are considered for this study. Data is highly imbalanced in a target variable, as only 339 machine failure records are found out of 10,000 records. Next, in the table, these are the columns considered for the study, as other columns were moved of the failures for the machine failure. Due to time and resources, we limit ourselves to classification of machine failure instances. First column is type. Column type helps us to understand the product quality variant, which is 50% low, 30% medium, and 20% high of all products. Means 50% of all products are low quality variant, and so on. Next is air temperature. It is a normal air temperature stored around 300 Kelvin with standard deviation of 2 Kelvin. Next is process temperature. It is calculated while machines are working with the values around 310 Kelvin with standard deviation of 1 Kelvin. Next is rotational speed. Values of rotational speed are stored using 2860 watt motor, and it is normally distributed with some noise in data. Next is torque. Torque is stored using same 2860 watt motor, and values are distributed around 40 Newton meter with standard deviation of 10 Newton meter. Next is tool wear in minutes. It is a time where tool is used in a process subject to wearing. And target column. machine failure, showing binary labels of 0 for the non-machine failure and 1 for machine failure. Figure shows data frame with 15 records. Column UID shows the tool ID, and a product ID column shows the combination of type of product quality variant and serial number. This is data pipeline where data is collected from UCI machine learning repository. Data is prepared for the reading using data frame and cleaning in terms of column dropping and other sanity checks. In EDA, univariate, bivariate, multivariate analysis from EDA is utilized to find fact about datasets and column behavior in terms of machine failure. In data preprocessing, we applied categorical variable transformation using dummy variables, identification of missing values using isNull function. Fortunately, there were no missing values found. Later, we did the outlier treatment on columns to prevent skewness of the data. Next, we did trend test split using sklearn model selection library and split the data into 70-30 ratio. We did feature scaling on xtrain and xtest. As a primary task classification, we applied few baseline models on imbalanced data and stored the results. Later, we used smooth oversampling method to balance the classes in the machine failure attribute. And again, we applied the same baseline models, logistic regression, random forest, artificial neural networks for classification on smooth oversampled data. The proposed multitask learning model setup is explained on the next slide. We applied MTL model on a balanced data and derived the results on a test data. This is proposed multitask learning model setup. Input is split into training and testing data, in which training data is fed to classification model and auxiliary model. Encoder from autoencoder will convert input into latent representation. Decoder will try to decode it with original data. Original data is compared with autoencoded data, and the difference between them is considered as a reconstruction loss. Primary loss of classification is added to the reconstruction loss, and combined loss is reduced using MTL model. To evaluate model performance, we have evaluation metrics. First is sensitivity or recall. Well, this measures returns the capture rate of the model. It says that out of all values positive class which were initially mentioned before, how many did the machine capture successfully? That is correct positive prediction to the total actual positives. Specificity or true negative rate measures a ability to correctly generated a negative results for a non-machine failures. That is correct negatives prediction to the actual negatives. Next one is false positive rate. This measures the ratio between number of negative events wrongly predicted as a machine failure instances to the total number of actual machine failure instances, that is incorrect positive prediction to the total actual negatives. Next metric is precision. This is also known as positive predictive value, which tells us that out of whole positively predicted records, how many are specified positive initially. That is correct positive prediction to the total positive predictions. F1 score is important when we have to reduce both type 1 and type 2 error. F1 score specifies a harmonic relationship between recall and precision. Next is misclassification rate, which measures the rate that how often confusion matrix is incorrect in predicting both actual positive and negative outputs. That is total incorrect prediction to the total predictions. Lastly, we have ROC and AOC. Receiver operating characteristic curve, and AOC is area under the curve. This metric is used to measure performance of classifier. The ROC curves explain the rate of true positive with respect to rate of false positive. Let's start with result and discussion now. Model output classification. To have understanding of model behavior, we implemented logistic regression model on imbalanced data. Accuracy of the model without class augmentation technique is 0.969. This gives that due to class imbalance, model is giving high accuracy. Later, receiver operating characteristic area under the curve came out as 0.56. Similarly, we applied random forest and artificial neural networks for classification on class imbalance data, received the following results. Later, we applied the same models on class balance data using smooth oversampling and found following the results. So this is the value distribution of machine failure before and after smooth oversampling. Moving to the next task, reconstruction of input. Reconstruction of input variable using autoencoder. This task in multitask learning is an auxiliary task which helps to improve primary task generalization by sharing representation, which helps to reduce overfitting. We have used mean squared error loss for this task. Following image shows the graph of mean squared error reduction using Adam optimizer over 100 epoch. Now, in proposed multitask learning setup, the MTL model is introduced with smooth oversampled data to have balanced learning. To reduce combined loss of binary cross entropy error and mean squared error, we utilize Adam optimizer. Following are the evaluation of the proposed model in our predictive maintenance dataset. We evaluated and compared multitask learning primary task results with other classification task results. Found MTL multitask learning performance is better than logistic regression and artificial neural networks, and good sensitivity recall and ROC-AOC score than random forest architecture. Due to generalization of two tasks, performance of multitask learning is affected compared to random forest F1 score, which is combination of recall and precision. Following figure shows that model evaluation of multitask learning setup and the total loss reduction in multitask learning setup. This slide shows individual loss reduction using multitask learning setup, classification using binary cross entropy, reconstruction of input using mean squared error.